So, today's topic is going to be about the PID controller and an additional controller design method, which is called the model matching controller. We actually did start on the PID controller last week, so this week we will be continuing on that. But of course, we have a slight different agenda this week. We are going to design a PID controller using the tabulation method, which we did last week. And then we are going to propose a PID controller, but as you can see here, it seems like we will have a result using the tabulation method. But then again, we are going to change something about the controller, some aspect about the controller, so that we are proposing a different controller. Once we've done that, it seems like we are again not happy with our choice, where we update our choice, our controller, so that we meet the requirements. In this case, we are proposing a controller. Now you can see that there's a pattern here. It's not a standard approach where you just have design a PID controller, design a different controller, etc., etc. But there's kind of a guideline, a pattern to it. So it seems like we will face some results and then another thing, and then we will just propose a controller. And the last task for today is going to be designing a controller using the model matching controller. But then again, we will be talking about what it is and how we do it and why we even need that. So yeah, let's dive right into it. Now we have a second order transfer function that looks like s squared plus 0.2 s plus 2501, which is the characteristic polynomial of it. And then we have our requirements as usual, where we are looking for 10% overshoot. And then again, not 4, but this time 2 seconds of settling time. Now I have already defined my transfer function using TF and the symbolic toolbox. I have the 10% overshoot and the settling time requirement here. Now, it is important to recognize the fact that when you have overshoot and settling time together, that means that you exactly know in what point you're interested in the S domain and on the root locus plot, probably. Because the overshoot directly relates to the zeta here, which is the damping ratio, which we've talked about. So we give it the minus log overshoot divided by square root of pi squared plus log overshoot. Again, here log is the natural log. Log 2 and log 10 are the functions with the coordinate basis here. And when we know zeta, when we have the settling time, we can just directly calculate what the value for omega n is, which is Ts times zeta. So when I run this, I can see that zeta is going to be 0.5912 and omega n is going to be 338. This means that we have a circle at the origin with radius 3.38 on the S domain. And then, of course, we have this zeta value here. If we use a cos d zeta here, this is inverse cosine, but in degrees, you will get 53.76 degrees. So that is going to be a line with this angle here. And the intersection with both the positive angled line and the negative angled line and the circle at the origin with omega n radius is going to be your design point or your choice of complex conjugate poles. You can, of course, directly conclude what the real value is going to be, because zeta times omega n gives you the real part, so it's going to be -2 on the real axis. And you can also take square root 1 minus zeta squared times omega n, which will give you the imaginary part, which is 2.72. So you can view this in the Cartesian coordinates, where you can see what the real and imaginary values are, or you can look at the polar coordinates, where omega n is the radius, and you can use the cosine for zeta to come up with the angle, and then you can also maybe transition into the tangent if you need it, and you can look at the polar coordinates. Now, this is the given point that we're interested in, and these need to be dominant poles, or this pole pair should be the dominant pole pair, and everything else should be away from it. So now, as usual, we are going to design the PID controller using the tabulation method, which means that I'm going to form the desired characteristic polynomial that I have in my mind which is s squared plus 2 times zeta times omega n times s plus omega n squared. So this is another way of saying that we want the specific point with omega n this value or zeta this value or everything that we've examined here. So this is the polynomial way of saying that. It's basically the same. But now, since we're going to design a PID controller, since we know that this is a second order transfer function, we know that the closed loop will be a third order transfer function, which means that we are going to introduce a residue pole, and the residue polynomial is going to be s plus p. So up to this point, we've basically come up with the ideal closed loop characteristic polynomial in our mind. Now we need the structure. So therefore, we need the controller parameters, kd, kp, and ki. These are going to be real values. The controller is going to look like, you can either use kd times s plus kp plus ki divided by s, which is a good representation. It shows you the derivative part, proportional part, and integral parts. Or you can just use kds squared plus kp times s plus ki, the whole thing divided into s, which is the transfer function form. It's basically the same. Now what we need is we need the closed loop transfer function, which is fss times gss divided by one plus fss gss. Now we're interested in pzs, pcs, which is going to be the numerator and denominator of our closed loop. So let's look at PCS. And as you can see, the highest order term has a coefficient of 100. And if I continue on as usual, like forming the problem using the coefs of PCS of all the S coefficients should be equal to coefs PDS times PES, all the S coefficients. And if I write down the whole set of equations, like this, it should be quite obvious that we cannot solve this problem. And in fact, if you ask MATLAB, you'll see that the solution looks empty. And the reason behind that is that our trivial equation, which is most of the time a trivial equation, is now a false identity. It's not an equation, it's not trivial anymore. And it's also not satisfied. So you can see 100 is not equal to 1. Therefore, we cannot solve this problem or use this problem as it is. Now, what is the reason behind that? Basically, we have a coefficient that we didn't take into consideration on the right-hand side. And the highest order term, s cubed here, has a coefficient of 100. But you can also see that it wouldn't change that much in meaning when we divide the whole left part or the left-hand side of the equations into 100, because then this would be equal to 1, this would be kd plus 0.2, this would be kp plus 2 or 25.01, and this would be ki. So it seems like MATLAB tries to conserve some accuracy here and therefore comes up with a value of 100 here, which is not that necessary. And probably the reason behind that is 2501 here, because yeah, if this would be 2500, I would suspect that we wouldn't have 100 here. So this is kind of the small toolbox trying to conserve or preserve some accuracy here. So what we need to do is basically, when we divide the whole polynomial, all the coefficients to a single coefficient or value, it wouldn't change the position of the roots or the location of the roots. So we can just normalize the whole set of coefficients so that the first term or the first equation is an identity or a trivial equation. So what I mean by that is I'm going to divide everything into 100 so I can get rid of this value here. Another approach would be to multiply everything on the right-hand side with 100, but I'd like to do it this way, where I take basically the coefficients here, which is going to be coefs. And then I normalize it so that coef is the coefficient vector here. where coef is the coefficient vector here, and where I normalize it basically with the first term, first element, which is the highest order term here. You can use this approach almost always because you don't really have to care about that. You can just normalize it whenever you want to be safe. So yeah, if it's not necessary, you don't really have to do it, but you can just place it and then just don't think about it anyways. Because if there's a coefficient other than 1, then it will be normalized with that. If that's equal to 1, it will not change anything. But doing this always might also cause some problems for some specific controller design problems. So therefore, I suggest you to check out what it is when you don't do this, or what it is when you do it. Sometimes for some controllers, this here would cause some issues. So yeah, keep that in mind. Sometimes normalizing is a good thing. Sometimes it's against you numerically, of course. So yeah, we have the coefficients, we normalize them, then we equate them to each other, which then changes the problem, which looks like this, which is solvable because 1 equals 1. Of course, in this case, we have 3 controller parameters, KD, KP, and KI, and then we have this residue pole, which is the 4th parameter, but there are 3 equations that make sense, or important, or are non-trivial, where this is an identity. So therefore, we are looking for tabulation because choosing one parameter as the parametric parameter and then solving everything in terms of that makes more sense because it will be much easier than doing it this way here. So yeah, we will choose KI because, again, in this case, it makes sense because I need to check what the stability of the whole closed loop is going to be. And since one of the poles is S plus P and the other remaining poles are already stable or on the left half plane, I should be careful about the value of P. And since P is directly relating to Ki and the positiveness of P ensures the stability, I can just conclude that Ki positive is going to end up in stable solutions. So I'm going to choose Ki because they directly relate to each other, and I can solve everything in terms of Ki because of that fact, because P is going to be Ki divided by 11.45. I can just plug it in here and solve Kp in terms of Ki, and the same goes for Kd. So let's choose Ki. Let's solve this problem for Kd, Kp, and P. We don't mention Ki, so the solution is going to be in terms of Ki. So now, actually, let me just display the whole solution here. Sol.kd, 4, like that. This is Kp, and this is going to be P. Let me also introduce a message screen here. There we go. So this is the set of equations, and this is basically each Kd, Kp, and P. Maybe we want to just display which one it is. Kd, Kp, and P. There we go. Now we can see that they depend on each other linearly, which most of the time I talk about. If you define your problem in linear coefficients when you're using the algebraic method, then it will end up being a linear problem. And you can see that, in fact, it is a linear problem. The coefficients relate to each other linearly. So now what is remaining here is that we will choose a vector for Ki, hopefully a global one, a big interval for Ki, and we will plug that in into these 3 variables here, and we will end up in Kd and Kp. Since we choose Ki being positive, we don't really care about P anymore because we know that it is going to be stable. So we can just focus on KD and KP, which will then again result in the controller itself. And well, then we can look at the step info data where the settling time and overshoot, if they're close to our requirements. And if it is, we're going to choose that one here. Before I continue here, something MATLAB specific that we did last week too is to convert these into MATLAB functions. Because they're linear functions, it makes more sense in terms of performance to choose them as MATLAB functions. You can also use the subs function here. It is okay. It's just not performance efficient, because if you have a for loop that is too long or that takes too long to evaluate, then you don't really want to have that. Whereas the expressions for KD and KP are quite easy to calculate with a MATLAB function. So I could actually also demonstrate it again. So maybe let's do that first. Let's choose log space. And the reason why I'm using logarithmic spacing is the fact that I want to look at very small numbers, 10 to the power of -1, and maybe 10 to the power of 3, even if that's excessive at this point. And I'm choosing 500 points. So I'm picking globally spaced points so that I don't miss the local optima that I'm after here. Because due to the nature of the problem, I might miss the local optima here because it's not globally optimizable. It doesn't need to have just one local optima. Or I might miss it actually. So it's the nonlinear optimization problem in this case. But we are approaching it in just one dimension because everything is in terms of Ki, and Ki is the only parameter that we don't know. It's quite an easy problem. If you don't use basically this approach, the dominant pole placement, then it would be a 3D problem. You would need to define a vector like this for each parameter, like KD, KP, and Ki, and this would be an R-cube 3-dimensional problem to solve, which is quite harder than solving it in 1D. So, and then of course we will have a for loop where we choose each value, Ki val equals Ki vector of I. At this point, what we can do is we can just calculate KP val equals double subs and then sol.kp. And then also for KD. Yeah, then we know what the controller looks like, namely KD val, KP val, Ki val, 1 and 0. And TS is going to be feedback, Fs times CS, 1. And then info is going to be step info. Then TSE, which is the experimental settling time value, is going to be info.settling time. Info.overshoot. Now, we also looked at this last week, but I'm just repeating it for the sake of reminding you of that. Well, at this point, we want to get the settling time value that is given here as a requirement. So TSE should be equal to TS, and OSE should also be equal to OS. But this is basically, and I have to divide by 100 in order to match this percentage here. Well, I want to do it simultaneously, but the first thing that I can do is just define some errors about that, like the absolute value between TSE and TS, and then the absolute value between OSE and OS. So these should be minimized, but I cannot combine them. They have different units, but if I normalize them to the expected value here, not TSE, not OSE, TS and OS, the specifications, then I will have a relative error here. And I can combine that into my objective, which is going to be 0.5 times E1, 0.5 times E2, and there we go. Now we could save this into a table. And it's going to be length of KI-VEC rows, because 500, so it should have 500 rows. And, well, we could just remind ourselves what we're going to save into it. So KI would make sense, KD, KP, maybe TSE, OSE, maybe error 1, error 2, and then the objective itself. So 3, 6, 8, I guess 8 columns should be it at this point. So then we're going to save this into the table, the ith row, all the columns. You could also do it individually. The first column is going to be KI val, and then so on and so forth. But you might also want to do it in one go, where you just say all the columns are going to be equal to this vector, where we have KI val, KD val, KP val, TSE, OSE, E1, E2, and of course the objective here. So once we're done with that, I actually want to time this too. We did it last week too. So tick and tock. This is going to display how much time it will take the CPU to calculate this whole for loop for 500 iterations. And now we want also to get the minimum value from the last column here. So minimum of the table, all the rows, last column, and there we go. Now let's open up a new figure and plot the KI-VEC versus the table last column here. X label is going to be KI. There we go. We could also indicate the point where we actually get the minimum value. That's going to be KI-VEC index. So KI val, comma, val is going to be the point of interest here, because that's going to be the minimum. Once we have that, what we can do is we can just get also these two values here. And then, of course, define our transfer function and get also step info like this. Don't divide by 100. And let's open up another figure to plot the results. Time is going to be YT. Title is going to be step response. And then the second one, which is going to be the pole zero map. So that's going to be sigma. That's going to be j omega. Pole zero map. And there we go. Now we need to step response. Y, T, step, TS, plot it. There we go. And then the pole zero map. Plot AX2, the real value of poles, the imaginary value of poles. And we could also display an S grid since we know what zeta and omega n is. And yeah, that should be it, I guess. So let's run this. Settling time is not spelled right, so settling. I'm not sure. Okay. Settling time. Still too many L's. Oh, okay. Cuts off this one here. Yeah. There we go. Now, since we used subs, it takes 3.3 seconds to calculate this, which is not a big deal. But if you increase that to 1,500 points, for some reason, if you want to be even more checking it more globally, and you can even increase it further and further, you will see that the subs function will slow us down because it will take too much time to calculate the whole for loop, which is not actually the case. It shouldn't be the case. We shouldn't wait for it to take 10 seconds or even more if you have a slower computer, if you're lacking SSD, etc. Then this time would increase. So instead of doing it like this, since this is just a linear function, I could convert it into it. Let's actually get the function using MATLAB function, which is a symbolic toolbox function. You just provided the sol.kd, and it should give you basically the MATLAB function, which is way is faster and easier to use than the function itself. So you're just going to replace this whole thing with just ki val as a usual function, and that's going to be it. And a function call is going to be way faster, and we'll see how. So let me also take it from here, use it here. So it took 10 seconds. If I run it again, it only takes 2 seconds. And of course, we're checking for too much points at this point. 500 points would be sufficient for this case. So it takes way less time to calculate it. So yeah. Now, yeah, we actually have our results, but what I still need to do is I'm going to just display the settling time here. String TSE, seconds, and then maybe overshoot, OSE, percentage. So that we see it takes 2 seconds of settling time, and it has a 2.46% overshoot value, whereas the problem itself was asking for 2 seconds of settling time, but 10% overshoot. And what we also observe from the figure here is that we actually have an interesting behavior going on here. And by the way, we have another figure which popped up in another display, which is this basically here. So yeah, this plot doesn't seem to be right, and the reason for that is the linear spacing on our x-axis, whereas we did actually use log space for it. For these cases, you might want to just change the axis of the corresponding plot, where you should just maybe set GCA the x scale. That should be log instead of linear. So if we run it again, now you would see it makes more sense to have it logarithmically. But then again, we see that there is an optima that we obtain somewhere here, and you can see the nonlinearity of the whole objective here. And we can observe that it is 10 to the power of 2. So it's about 100. So Ki is about 100 something. So what we could do is we could then conclude that we might want to switch to linear spacing back again, and then maybe between 50 and 150, choose 500 points, but this time linearly space it and give me the result basically. So run it again. There we go. We end up in this small point here, which seems to be optimal. Now we can see on the S domain that the omega n value 338 was the natural frequency that we were looking for. 0.591 was the zeta value, and you can see 53.7 degrees should be this angle here. And the intersection of these two gives us the point of interest, or our complex pole pair. Then again, we have the residue pole here, which seems to be away from the dominant region, which is a good thing. Seems like it is around 9.39. Then we have value 2, a 4.5 dominance factor. The ratio between the real value of this and this here is 4.5, which is not bad, which is good. But you can see we have actually a dominant 0 pair, which is not what we wanted, which is causing us the problem, and which also ends up in this weird shape of a step response. Now, yeah, if you would have just wanted to boil some water in a kettle, for example, you would just plug it in, start the kettle, and you would wait for some time. And then if this was the design of the kettle, you would experience something like this, where in just how many seconds? 0.8 seconds. In 0.9 seconds, you would reach basically 90 degrees, and then the kettle would shut down, and it would wait to cool it down a little bit, and then it would just increase the or it would just increase the degrees again to boiling point, where it would reach it in 1.5 seconds, and then it would just overshoot a little bit, and then it would be around 100 degrees Celsius. So boiling water like this, of course, here time is in seconds, but maybe this is in minutes, then it makes more sense for a kettle because it takes some time, and it's not possible for seconds. But you get the idea. Boiling water in this shape would be weird, because you would just continue boiling and then just leave it at that degree, and you would be happy with that. You wouldn't want to have something like this. In terms of the electric bills, if you have this boiler in your kitchen, you wouldn't be happy, because, well, there's a very steep step response reaction here, which means that you will be having very high current values, and that would just give you high bills, which is not nice. Yeah, and this actually also forms the basis of dominant pole placement. Most of the time in real world applications, we want to get a first order or second order degree responses. We want to see that shape most of the time, because it's more optimal that way. Boiling water, well, just have a first order system that rises to for example, takes 1 minute to rise to, I don't know, 86 degrees, and then in the second minute it would be 90 something. In 4 minutes it would be ready, and it would be boiling. So that makes more sense in terms of economy, control effort, and the shape of the response and everything. And this one here wouldn't make sense. So this would be wasting money, wasting control effort, and it would be weird. If you're in a car, in a vehicle that accelerates with this dynamics, you would be homesick, you would be sick probably, because yeah, you speed up too much and then you just decelerate a little bit and then you accelerate back again. It's not ideal as a shape. For systems that have these complex maneuvers, you wouldn't use dominant pole placement like F16 or some I don't know, plane dynamics. Then you might want to end up in these acrobatic performances, and then you need that nonlinear dynamic, nonlinear behavior. That would make sense. But for other applications, practical applications that we address in this course for now, they should behave like first order or second order systems. The downside to a first order behavior is that it doesn't overshoot, and the second order behavior just gives us that. And here it seems like we're failing in that sense. It has this weird interaction, and we're not happy with it if we are designing a system that should be controlled with dominant pole placement. So I hope that I could give you the clear picture here. This dynamic is a weird behavior. We don't want it for most of the time when we're using dominant pole placement. This would be only possible with high order systems, and those high order systems might be special systems. Maybe that's a rocket you're launching and you need to have too much power at first to just get out of the gravity effect, and then you can just slow down because you're losing your module, etc., etc. So in complex and high order systems, that make sense. It may make sense. But for systems with first order, second order dynamics that we're trying to model here, this is not acceptable. Well, but the problem here is that we actually have optimized it in terms of settling time and overshoot. And you can see that the settling time is exactly equal to 2 seconds, but we didn't match the overshoot requirements. But it seems like this is the best that we can get here. But I would argue with that, because you can see that here's a pole pair, here's a zero pair, and then there's this pole here. So if they would have been closer to each other, what we would experience here is would be that this would be more like a first order system, because we've talked about pole zero cancellation last week. And if that would occur here, if this pole zero cancellation of a pair would happen, then they would just get rid of their effects, and we would end up in just this pole alone. So actually, the question is kind of asked in a special way, so that you should basically conclude or try basically to come up with a pole zero cancellation controller here. So we designed a PID controller using the tabulation method, and it seems like the global optima seems like this point here. But what we can do is, since they're close enough to each other, we could propose a controller, PID controller, based upon the poles of the system, and just try to get rid of the poles of the system. From last week, we had actually 3 real poles, and we were choosing 1 or 2 of them to get rid of the pole zero, get rid of the pole of the system with a 0 of the controller. And then we were trying to design a controller with the remaining stuff. But here, we actually don't have that choice, since we can see that there is no real pole here. In fact, we have a system that should behave interestingly. We know what the characteristic polynomial looks like. So what we can do is we can assess the behavior of the system. We know that 2 times zeta omega n, 2 times zeta times omega n should be equal to 0.2, and omega n squared should be equal to 25.01. So if you think about it, this is like 25 divided by 10 to the power of 2. And if you take the square root of this, it should give you 5 times 10 to the power of minus 4, I guess. So the square root of 25.01, the square root of 25.01 gives us basically 5.001. So this is basically omega n. And 0.1 divided by omega n, it's 0.02. So zeta is going to be 0.02. Now, based on this information only, I could conclude that the system has a very low damping ratio, in fact, almost equal to 0, which means that we have high oscillations. And also based on the fact that the multiplication of zeta and omega n is equal to 0.1, it would take 40 seconds to settle down. So the system has high oscillations. It will take 40 seconds to settle down. And well, the frequency of these oscillations are 5 radians per second. And in the steady state, I can also conclude that 1 divided by 25, which is 0.04, I guess, roughly, this is going to be the value where we settle down. So in steady state, it should be equal to 0.04. So we have a very interesting system at hand, and we're trying to design a PID controller to it. So when we have GS, when we open up a new figure and look at the step response of it, you will see that our assessment is in fact correct. Let me bring it up to the display. There we go. In the steady state, it settles down to 0.04 approximately. It takes 40 seconds for the oscillations to settle down. And yeah, the frequency is high, and we know for a fact that the frequency should be 5 radians per second. Now, for this system, we're designing a controller. It is important to know what the open loop system looks like and how it behaves because, well, in this case, when we're trying to get rid of these pole pairs, we should be careful because we are somewhere along the j omega axis and we're near to it because 0.02 or 0.02 is close to 0. So this zeta value here is not that big. Yeah, let's propose our controller. And the controller that we're looking for is going to be, again, a PID controller. So let me just state it for B. And well, usually I would like to go ahead and, yeah, let me just choose this one here. I need to define my controller, K times this divided by S. And the reason behind that is I'm going to choose a 0 pair on top of the pole pair of the open loop system. So since the root of this is going to be the complex conjugate pair, I can just directly choose this polynomial here. I would be canceling out the denominator of the system. And I have to add an S at the origin because it's a PID controller. Now you can see when you know the location of the zeros, and since you will know that you're adding a pole at the origin, you are done with the dynamic part, which only leaves us with the p-type controller part of our whole structure here. So the only unknown is going to be k, which is going to be a real value. And well, we can look at the closed loop here. Like this. And it would immediately show us something that we already know. Namely, the closed loop is going to be k plus s. Now, we did cancel the poles of the system with the zeros of the controller, and we added an additional pole at the origin because the PID controller structure says so. And then we have this gain, which is the only thing that we didn't decide on. And this gain relates directly to the pole, to the location of the pole. And yeah, it's a first order closed loop because 2 poles and 2 zeros cancel each other out. You can see we place these zeros on top of this pole pair, which means that they will cancel each other out. And the only thing that is left is going to be this pole, which will be decided with the gain k. So if I'm going to satisfy at least one of the specifications, which is the settling time in this case, because I cannot obtain overshoot or result in any overshoot because the closed loop is a first order system. So I should basically choose maybe k equals 2. So that would give me roughly 2 seconds of settling time. So let's do that. Let's choose k equals 2. Therefore, our controller is ready. It should be, let me just take this one here. So Fs is going to be 2 times this divided by S. So now I can repeat this stuff here. Since my controller is ready, I can just copy the whole thing here and paste it here. Yeah, let's have figure 3. Other than that, we should be good to go, I guess. Yeah. Let's run it. And there we go. Well, maybe I should adjust the x limits to -3. Let's run it again. Here we go. A bit better. So let me just zoom in. Now we can see the setting time is almost 2 seconds. You can just increase it or decrease it a little bit. Doesn't really matter. You have 2 seconds of setting time, 0% overshoot. And we can see the pole zero cancellation is happening here. And we are on the real axis -2 because that should be the real part. 4 divided by the real part of our pole or pole pair gives us the setting time. So we're on the same line. We have the same setting time. Now, if we are trying to use dominant pole placement, we would prefer this shape over this one here because it takes a nice curve. If you're boiling water, this is the best and most efficient way of boiling a water. It takes, I don't know, maybe 4 minutes and then it just boils. And this is the ideal electric bill kind of thing going on here. Whereas here we have a weird behavior. It's not suiting our requirements most of the time. Of course, this is not exactly what we want because we have a specification that is 10% overshoot, but at least we don't have this weird shape of a step response that we have here. Now, yeah, actually, I want to show something here because we rely on the fact that the pole zero cancellation happens here exactly. We might want to introduce some modeling errors to our actual system and observe what really happens to our closed loop for both of these designs, because here we don't really rely on the cancellation and the step response is already bad, but here we solely rely on that and our step response looks quite good. What happens if we introduce a little bit of an error to the model? And yeah, let's see what really happens here. Let me just copy this one here and let's say, I don't know, GSH something. And let's toy around with these numbers here. Instead of having 0.2, let's have 0.18. And let's have, I don't know, 26 exactly instead of 25.01. So I'm going to calculate, I'm going to repeat this part. Yeah, let me just take this one here. So this is going to be using this one here. And then I'm just going to plot these here. So now let's give it a different color. Let's match the color. And that should be it, I guess. Let's do this for this one too. And it should actually work, I guess. So nice. Now we can see what we're really trying to do here. If the pole zero cancellation, for example, for our latest design here, doesn't happen really on top of each other, if it's not exact, you can see they're kind of close to each other, but they're not exactly on top of each other. Then you can see we have these oscillations going on, which is quite bothering us because this is most probably going to happen in a lab when you're trying to realize the system. If you're trying to design the system and, as a practical application, you will face this problem if you have the system and this PID controller, because in the real world, nothing will cancel each other out perfectly. It would be around the vicinity, but it would be close to each other, but it wouldn't be on top of each other. Then you would end up in this weird oscillation stuff, and yeah, you wouldn't be happy. Here, we still have this weird behavior, but it doesn't really matter because it wasn't really relying on pole zero cancellation at all. So yeah, it's actually way better than our design if you think about it, because this one is more close to its original design, but this one here has a big issue where it starts to oscillate, and I suspect that this would go on for quite a bit, like 30-40 seconds, because it stems from the open loop. It comes from the fact that the open loop has high oscillations. And this approach here, what we're trying to do by canceling poles and zeros, or by using this kind of pole zero placement here, which occurred naturally, of course, we didn't really decide on that, is actually something special. And it's called the notch filter, which is basically a band stop filter, and which tries to stop the filter for frequencies, which tries to stop the frequencies for omega n, well, you guessed it, equals 5.01, because that's exactly what the frequency of our open loop oscillations are. So we're trying to kind of control a system that has high oscillations in it for high frequencies, and we're kind of trying to design a low or step response, or low frequency design. So our design point is a low frequency point, but we have high frequency modes in it. Therefore, what the optimal solution seems to be in this case is to use a notch filter, where the notch filter tries to band stop the frequencies of the open loop system. And well, we are trying to then add some poles and zeros so that we get our wished behavior. And you can see, well, it's not quite nice to cancel them out if they're not on top of each other. It has a slight difference, and it's quite negligible if you think about it, because they're quite close to each other. It doesn't really matter in real life if it's 0.1 or if it's 0.18 or 19 something, because they are almost exact values. You will have noise, for example, for all measurements, and you will never be able to measure that ideal value. So yeah, that shouldn't be an issue here. But it seems like the design has some problems if it's not canceling each other out. Yeah, we could toy around a little bit more. Like, let's have higher frequencies. What happens then? You can see the oscillations, they increase even a little bit more. Let's drop down. Let's, I don't know, place it like this. And you can see we could even reach instability, which is quite interesting, which you might not have expected. But it is in fact not stable. And the reason for that is that the pole zero cancellation happens around the j omega axis. And you can see it could pass through the j omega axis, and it could also be unstable. Yeah, it is dangerous to work around the j omega axis, and that's exactly where we're working here. Therefore, we should be careful about that. And the best solution that we could come up with here is to be a bit conservative and try to place it a bit to the left of the zero here, because a root locus occurs here, and if the branch crosses j omega, then you're in trouble, basically. So what you should do is you should be trying to aim at this region here to place your zeros, so that the pole is somewhere here and the zeros somewhere there, so that the branch occurs somewhat in a safe zone and not crossing the j omega axis, which is quite difficult to do if you don't know the model exactly, which is most of the time the case. So yeah, this is of course a little bit too much. This would be a better choice here. Even that one did not work. We need to have closer omega n values to get the effect that we're looking for. So of course, practically we have solutions for this. We would just have a filter with our measurement unit. We would embed this filter structure into it we have to work around with that, and we would be happy with this shape, for example, if it's the best we can get here. You can see there's no problem of stability, no problem of anything, whereas here pole zero cancellation seems to be a bit troublesome. But still, in our course for now, we know that we're canceling them exactly because theoretically that's possible. We would assume that the blue one here is a better solution than the one on the left, because theoretically the cancellation is perfect. This is also important because pole zero cancellation on the right half plane is not acceptable at all for the same reasoning. The pole zero cancellation might not occur on top of each other, and then you would have instability in your closed loop. That is not something that we want. And the same goes for here. If you're near the j omega axis, you should be again careful with your cancellations. Whereas if the pole zero cancellation happens more towards the left, which is not even close to each other, and for example, if this is the structure, then you can see we're much more safer in terms of modeling errors, because yeah, at least they are going to be stable modes. It will mess up the whole shape of the system response, but we would be happy with that instead of having something that is not stable. Well, let's go back to our original discussion. We were looking for the design here, and we've seen that when we use a PID controller, it is possible to get something robust but weird in shape, or we could just have this first order transfer function model where we cancel out the pole zeros with each other. But the requirement is not only to have the settling time equal to 2 seconds, but also have to have an overshoot of 10%. Well, how can we basically do that? Now, the next question is all about that. So propose a different controller that is based on the PID controller, but correct something that the PID controller is not capable of, namely overshoot. So now, when we look at our response that we did come up here, let me just copy the whole thing here. That's going to be C. Now we can see that just one pole here doesn't cut it, because the closed loop is going to be a first order one. So what we can do is either you could just see directly what you should place, which I in this case can, and I'm going to do it. Or you might want to go the safe route where you say, okay, I don't know where I want to add this pole, but I know that I'm going to add another pole to our controller. Now, ideally, you would end up in S times S plus P. But if you think about the root locus of this whole thing, we have K times the numerator, which is going to be also the denominator of the system, divided by S times S plus P, and then times the system, which is 1 divided by this polynomial. So this will cancel each other out. We will end up in K, S, and S plus P. So if you neglect K for a moment, you would see that the opolar poles, or the loop poles here, would be one at the origin and the other one would be at minus P. So since there are going to be only 2 poles, no finite zeros, everything is canceled out, we would end up in a root locus that is quite familiar to us. It starts from 0, starts from minus P. They coincide at minus P divided by 2. Then we have our asymptotes, and they will tend to J infinity and minus J infinity. So, and we know that this J infinity minus J infinity should occur at minus 2, at sigma equals minus 2. Why? Well, our settling time is going to be satisfied, and that settling time lies on this line of minus 2. So one at the origin, one somewhere on the left half plane, they should coincide exactly at minus 2. If that's going to happen, I should choose P equals 4. Because then I would have S plus 4, so 0 and minus 4, they coincide at minus 2, J infinity minus J infinity. And then when I have 53.7 degrees of an angle for zeta, then that there somewhere should be my solution for K. So I can foresee what the root locus is going to be. And based on that, I can also come up with the exact value of this one here. But let's go the safe route. Let's assume that you didn't think about it, and you just assume that you have to add another pole to it so that your closed loop is going to be a second order one. So let's switch this to change this to 4. Let's close this whole thing here. And let's look at PCS. Now you can see that the model looks like S squared plus PS plus K. And since this is just a second order transfer function or second order characteristic polynomial, and due to the algebraic methods, you know that you're just going to equate it to PDS. You can see that you can just solve this problem. S squared equals S squared, PS equals 4S, and you can see P is equal to 4. And K is going to be this value here. And that's it. So I'm just going to basically take this part of this one here and solve it to get it numerically. But I already know what it is, but I'm just still going to do it. Now the problem is going to be coefs of PCS S all should be equal to coefs of PDS S all. Display the problem, solve the problem for whatever it is, and show me the solution. So there we go. K is going to be this one here. P is going to be 4. So let's actually determine what K val is. Double sol.k. Now I can state my new controller, which is using K val, and which is basically using another pole, which is one of them is at the origin, one of them is at, let's say, P val, and also solve P val maybe. But I already know that this is going to be happening at 4. So once we've done that, we can just open up everything else and see how it behaves, basically. Now, this is figure 4. Now, before I go on, I'm just going to get rid of the modeling error, and this is basically our step response that we acquired here. We can see we have 2 poles here, and we can also see we have a pole zero cancellation exactly here. So there are, technically we have 4 poles and 2 zeros, but a pole zero cancellation for a pole pair happens. Therefore, we end up in just pure 2 poles, and we choose these poles so that we have the settling time and overshoot requirements as we want it to be. And we can see on the left half, we have 1, P, and K, which is basically the characteristic polynomial, and on the right half, we have right-hand side, we have PDS, and we've just chosen P and K accordingly. So we kind of propose this controller, which is a second order controller, but has a pole zero cancellation, and it just basically gets rid of the poles of the system, original system, and places some poles so that it gets the job done here. So hope that you can see the pattern here. We looked up, we used the tabulation method and designed a controller. Then we've seen that, well, pole zero cancellation could be a thing. Let's try that out because it seems like it is almost there. Why not try it directly? We've proposed a PID controller based on that. We've seen that it works, of course, with limitations, but still it works. And we didn't match the overshoot requirement. Maybe we should add another pole to the controller so that we have 2 poles, they coincide to each other, in each other, and then generate the second order behavior where we can choose the parameters accordingly to get the requirements and basically satisfy the requirements, and that's basically what we got here. Of course, we've seen that when we again introduce some modeling errors, we still mess up stuff here, and it is what it is. We cannot change that much about it. We will have these oscillations for quite some time, and you can see it fades out in 40 seconds because that's the system that we have. Yeah, this is basically the design that we can come up for this system. If the pole zero cancellation is not exact, then we are in trouble. But other than that, we can just use pole zero cancellation. So it's a bit problematic. Of course, we should just look at it like a good filter plus PID controller maybe. And that's almost what we did here, because we kind of have this filter structure here, and then we added maybe some poles and kval to add the controller part to it. Yeah. Now, the last task here is to design a controller using the model matching controller. Before we do that, I have to introduce you to the model matching controller. Now, it is not something new, actually. It is something that should be familiar once we've covered it. And it goes something like this. We know for a fact that we are looking for a PDS, and we hope that our controller structure and the system combined should give us a closed loop transfer function that kind of mimics PDS. Ideally, we want to have just PDS and no zeros, so true poles and no zeros, but that's not happening most of the time because we have higher order systems and higher order controllers. Therefore, we might end up in poles and zeros. The best what we are trying to achieve here is to just have two poles that are dominant, and we're trying to push everything away from the dominant region as far away as possible so that it nears the behavior of a second order system. But in model matching, since we're at it, since we know what PDS should look like, what we try to do is we try to come up with the ideal transfer function. Usually that's a higher order one when we fix the controller structure, but we forget about the controller for 1 second, and we just focus on the closed loop transfer function that should be obtained ideally. And for that, we already know that, for example, the characteristic polynomial here of this should be 1 and then 2 times zeta times omega n and omega n squared. So that's not something new. So we know that for a fact. But we are proposing a polynomial, not a closed loop transfer function. So therefore, if we are trying to state a desired sort of transfer function, since we're looking at problems with reference tracking, it seems like we should add it some numerator that would end up in perfect reference tracking. And if you think about the final value theorem and the fact that we are looking for step responses, it should immediately pop up that the numerator should match basically the constant term here, so that s equals 0 will get rid of these terms. Then omega n squared divided by omega n squared should give us gain 1, which corresponds to y divided by r equals 1 in steady state, so that y is tending to r. So reference tracking. Therefore, our ideal closed loop transfer function should look like this or behave like this. Most of the time, we have additional poles and additional zeros, but we hope that they are far away. For example, one suggestion might be when we have 1, 0, that the 0 should be far away, let's say s plus 20. But of course, then the gain will be modified here. So what we can do is we can just have 1 divided by 20 plus 1. So if you add a 0 like this, this is out of the dominant region, and therefore it would be basically okay to choose here. Of course, 20, assuming that zeta omega n is something like 1 or 2. So yeah, then it is out of the region. It might be in the region. So something better would be like 10 times zeta times omega n and stuff like that. But yeah, you get the idea, out of the dominant region. But for our model matching controller, we just try to come up with this exact transfer function. Now, the question is actually the following. Instead of using a fixed structure controller with the system in a feedback loop to end up in the best dominant setup as possible, what is the controller structure or the exact controller that gives us this ideal transfer function? So now we don't know what the controller looks like, but we know what the closed loop looks like. And we know what the system is. So therefore, we are going to work out what the controller should be. And it's quite easy because we know for a fact that fs times cs divided by 1 plus fs times cs is going to be our closed loop. And if this is equal to TDS, then we could maybe work out what fs should be. Namely, when we multiply everything with 1 plus fsgs, we would end up in this equation here. And furthermore, we could get rid of these parentheses here. And this would then be converted into TDS plus TDS times FSGS. And this term here has FS, so let's move it to the left. And I guess you see where I'm going with this. So this is going to be 1 minus TDS times FSGS equals TDS. So basically this would end up being like TDS divided by 1 minus TDS. It is equal to FS times GS. Now, before I continue, I'm going to define TDS divided by 1 minus TDS equal to LDS, something that is going to be important in a moment. And the reason why I do this is basically the fact that LDS divided by 1 plus LDS is something special. So let's use this definition here. I say that this is LDS. I'm defining this as something new. But if you look at LDS divided by 1 plus LDS, what you're going to end up in is this divided by 1 plus this here, basically. Now, it seems like a bit confusing, but actually, let me maybe bring it down like this one here. So you can see that we have a common term 1 minus TDS. If I multiply with that, we would end up in TDS divided by 1 times 1 minus TDS plus TDS. So 1 minus TDS plus TDS. And this term will cancel out. So if you look close at this, this is nothing else than TDS itself. So these will get rid of each other, and TDS divided by 1 gives us TDS. So in other words, if we have something like TDS divided by 1 minus TDS, if TDS is the closed loop, LDS is going to be the loop transfer function. And if you use this loop transfer function to calculate the closed loop again, you would end up in TDS itself. So that's an important property here. And we are going to see why that is important. Now, for this reason, what we are actually looking at here is, in other words, LDS. So we know what TDS looks like. We know that it should be omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. We can use this and transform it into its open loop version, which would be, I guess, 1 divided by 1 plus 2 times zeta omega n s, something like that. We'll see it in a moment. And that's basically it. Come up with a controller that kind of multiplied with the system gives us the open loop that we are looking for. And that's basically it. Now, of course, one step further, in order to make this transition from Fs times Cs equals LDS to Fs equals something, we need an assumption here between 201 and 202. And it is that GS or its inverse should be stable. So I'm going to take the inverse of the transfer function, so times GS to the power of -1, but with the restriction that GS is a stable transfer function and its inverse is also a stable transfer function. So that would mean that both the poles and the zeros should be on the left half plane, because when we invert a transfer function, poles and zeros switch places. So now this is basically it. This is the controller, and this is an alternative expression of the controller. So basically what we could say is LDS divided by GS, because we are using SISO, and this GS times 1 minus TDS. So line 201 and these two lines are explaining to you what the model matching controller is actually. Now, the interesting thing here is that once this is your controller, don't forget that we are actually using the multiplication fs times gs divided by 1 plus fs times gs. So we're multiplying our controller with the system itself. So if you multiply the controller with the system, you will have pole zero cancellations. And in fact, all the poles and all the zeros of GS will be canceled out. So until this point, we've seen some partial pole zero cancellations. But today we've seen actually that all the poles are going to be canceled out with the controller zeros. And this is exactly the same. So it takes the inverse of the system, if it's invertible, and then it uses it as a structure. It's the part of the controller, and adds more to it in terms of poles and zeros, and that's going to be the controller itself. Or in other words, it converts the closed loop into open loop and then uses that open loop divided by GS because it should get rid of GS entirely. So the model matching here happens when GS and divided by GS, so basically the inverse and GS itself, is multiplied. Because this part is in the controller and this part is the system itself, this should be happening exactly. So this is basically pole zero cancellation at its best, because everything is getting rid of everything. All poles are canceling the zeros, all zeros are canceling the poles of the system. So the whole system vanishes. It's a part of the controller. And then you'll add some extra stuff so that the closed loop is as desired. So yeah, and it is quite easy to design such a controller. You only need to come up with TDS, or I could also come up with LDS, which is TDS divided by 1 minus TDS. So let me just comment this out and show you what this gives here. Now you can see that LDS seems to be something of high order, but you will see that it is not. Basically, it's just the cancellation of s squared plus 4s plus 1145. They are both in the numerator and denominator. So if I want them to vanish, I'm going to use min real, and that should solve the issue there. And I will end up in LDS. So 11.45 divided by s squared plus 4s should be the open loop if I want to get TDS. And since LDS divided by 1 plus LDS, or feedback, LDS comma 1 is going to be TDS, you can see this is basically TDS. So I'm converting the closed loop, desired closed loop transfer function, the ideal transfer function that I have in mind, I'm converting it into open loop, because once this is the open loop, the closed loop will be TDS. Then the only thing that's remaining here is to just choose FS LDS divided by GS, and that's it. FS is going to be the following here, which is exactly this one here. Now, the interesting part here is, of course, the following, because if you look closer, this should look familiar. Remember, we have designed a PID controller that gets rid of the zero pair, the pole pair of the system, GS, with a pair of 0, which was exactly this one here, s squared plus 0.2s plus 2501. And since we were looking for a PID controller, we had s and another coefficient here. But then again, in C, we decided to just add another pole, and that pole should have been at -4, so that we get the exact root locus that we were looking for. So you can see that this is basically the answer of the previous question of C that we had here. So let me show that one too, because we didn't write it out. So in C, before D, I'm just going to place ZBKFS, and you'll see that we came up with the same controller here. That's the controller that we've designed or proposed, and this is the controller with model matching controller, or model matching, using model matching. And once we multiply this with GS, we will get rid of this here, because GS is exactly that. For both in C and D, we've designed a controller that gets rid of the system, because the inverse of the system is going to be just this polynomial. So 1 divided by GS. You can see this is just the polynomial. And this is in the controller itself. It has its subcomponent, which is basically the inverse of the system. So here, what I can add to this is that we once talked about something like GS is inverse, and then the system itself. This is an open loop control strategy where you are using basically the inverse of the system, or this is called control with the inverse of the system. And we did it in many different ways. For example, since this is the model of the system, what we could do is we could just design a controller like this, or we could just design a controller like this. Both are open loop strategies, and both are just going to work for open loop strategies as it could be. So the maximum that we can do here is just adjust the DC gain of the system, so 25.01, or we could add the whole dynamic. So when we apply input to it, it would just get rid of the system. So R and Y should be the same. But when we have disturbance, when we have measurement error, when we have something, or when we have modeling errors, nothing will update itself because there's no measurement, because this is open loop. But model matching control is kind of the same, but it does it in closed loop. So that's the only difference here. We have basically this cancellation here. So we have basically the controller that has some part of it, FS1, and the inverse of the system divided by GS. And then there's the system, but then we have this feedback loop, which changes everything here. So it's something like this. Even though we get rid of GS and GS's inverse, we have some subpart of the controller, it will end up in a closed loop. And since we're measuring and doing stuff, and you can also see that LDS has an integrator on its own. So we had LDS. So you can see ZPK LDS. It does have an integrator at the origin, which increases the type of the system, because you need open loop pure integrators or poles at origins to track references for step, parabolic, etc., etc. It pops up directly, so you can just assume that the model matching controller will always track references for step type inputs. If you want to, of course, have ramp type input tracking, you should update TDS here, so that you have basically 2 times theta omega n s plus omega n squared. So that in that case, you would have s square at the origin. You can just toy around with it and see if it's really the case. But you can see this is something like control with the inverse, but in closed loop. And it relies on the model of the system, as it was the case for control with the inverse here. So we know this as pole zero cancellation, but in this case, for our today's discussion, it seems to be the exact same here, but that's not going to be always the case, because, well, here we had no choice but to get rid of the whole system dynamics, which is just the high frequency part of the system, and there's no other choice. But previously we had 3 poles, 3 real poles, and if you don't cancel all of them, then it's not the model matching controller. It's going to be partially model matching, because it relies on some part of the model, not all of it. So the difference here is that you have to get rid of the whole system, and that is implied here by this equation here, or also by TDS, 1 minus TDS divided by GS. So divided by GS means the whole inverse of the system. All the poles, all the zeros of the open loop system are going to be canceled, and we are going to add some additional stuff to it so that the closed loop is what we want it to be. So this is actually it for this week. Let us recap what we did so far. We did look up the zeta value, omega n value. We formed our PDS, and then we defined our controller linearly in terms of polynomials. And then we looked up what the closed loop looks like. By the way, in the PDF, you should also have this in your notes. I've shown you that there's a direct calculation method when you have just pen and paper and maybe the matrix inverse calculation capability. Then you can just opt for this automatic solution here where you have the residue coefficients, the controller coefficients. You just leave Ki as something that is known. You choose Ki as the parameter, so everything is going to be in terms of Ki. And we have D here, which is going to be basically the shifted PDS coefficients. And then we have minus P, which is going to be P1 and P2, the relation here. You can look it up. It's just generating you a matrix structure so that you can just directly get what MATLAB Solve would give you, or you don't really have to do this. You can also work it out on your own by just giving the set of equations. I seem to have skipped on that, but you can see here we have the set of equations. So let's find out what KD, KP, and yeah, P is in terms of Ki. Of course, you might want to choose your residue polynomial as E1 S plus E0. We most of the time know already that E1 is equal to 1. So therefore, we skip that part. But in its most general form, it's E1 S plus E0. But we know that H is going to be equal to 1, so we skip that most of the time in MATLAB. But you can see E1 is already 1, so it's going to be the same. And this is probably the inverse of 11.45, so you can work it out yourself. But sometimes this is this becomes handy because in classical exams in the previous years, you might want to use this because then there's somewhere some matrix inverses, and one of them is used for this directly here. For example, you see in the paper that there's a specific matrix with its inverse. Inverse is equal to this here, so basically this one here. And then you just plug that in and you move on, or you have to do the calculations by hand. Not the matrix inversion, of course, but I would rather do the direct relation solving here out of these equations. Yeah, whatever. Now, I've just added for your information, but of course, I'm using MATLAB to solve that. This is, again, a very bad tabulation method. I'm always going to keep this here because this is the bad version. I have shown you the better version where you can just track the results way better than this approach here. And you can see in the PDF, I have actually given the root locuses too. This is the open loop poles, which are close to j omega, which we worked out. And we are adding two poles, which are the poles of the PID. I'm sorry, the zeros, the complex conjugate zero of the PID, and then we have a pole at the origin. And this is the root locus, and you cannot avoid having a pole pair and a zero pair so that they are near to each other and can cancel almost each other out. That's not avoidable for a PID controller. You can see that based on this PID, this root locus here. And the best what you can do, which will, of course, mess up your settling time of your system, is to try to increase this gain value so that you match pole and zeros here. But then again, that's not the best idea. Instead, we should maybe place them on top of each other. But then again, when we do that, we get this root locus here where we have just one pole, and when we increase the gain, the pole tends to the left. So we choose it so that we have 2 seconds of settling time, and that's going to be the PID controller with pole zero cancellation. But of course, this is a special structure, as I've told you before. This part here is actually called the notch filter, so we are kind of ending up with a filter plus controller type of a thing. But yeah, this doesn't satisfy our requirements. We have to add another pole. When we add the pole at -4, due to the symmetry, it would go to J infinity and minus J infinity, and this would be the line that we are interested in. Then we can just use the intersection with theta, and this point would be then corresponding to a certain gain value, which we've then calculated and designed our controller. If this cancellation is done, we can see that it is kind of a second order transfer function, and that's exactly what we're looking for here. Now, the model matching controller, I've given you these steps in more detail. We just get basically TDS divided by 1 minus TDS, which is the open loop transformation, and divided by GS is just the inverse of GS. Poles of GS are zeros, and zeros of GS are converted into poles and embedded into its controller. And I didn't really bother to look for the step response and stuff like that, because we already know that this is the same result as the previous one. But you can see it's basically getting rid of the poles, zeros, and it's placing something at a pole at -4. It has a pole at the origin, and we are basically doing the same. We're repeating ourselves at this point, and this is the best we can get here. Now, as for conclusion, we can say that the model matching controller, the way that we've come up with the model matching controller, gives us a result that works theoretically. But in practical applications, this is very dangerous, and it's a topic that should be handled carefully, because we're around the j omega axis, and a pole zero cancellation around the j omega axis is quite dangerous. As you have seen, I've just fiddled around with the model parameters, and then we ended up in instability, we ended up in bad behavior. So the best that we could do is to embed a bandstop filter. That would make more sense. Of course, the filter dynamics are included to the behavior of the system, so that limits us kind of. But theoretically, we could just say, okay, this is the best controller that we came up in CNT, but it is dangerous because it's around the j omega axis. If we were in practical world applications, if this doesn't work, we have to opt for the one in A, which is way better performing in terms of modeling errors and stuff, but the shape is a little bit weird. So yeah, that is basically it here. So hope that this week was helpful. Hope that you gained a perspective on PID controller, because that was the aim of today. We actually know what a model matching controller is, and it's quite easy to come up with one, but you have to get the philosophy of it, the point of view of it, and not the formulas, because it doesn't really matter. And we're using it most of the time partially, and it's also possible to come up with a model matching controller. But the problem here is that it needs to get rid of the whole system, so it would be at least equal to the order of the system. And we are adding poles and zeros to it, so it is a high order controller method, so it comes up with high order controllers. For this case, it was a second order controller, which is okay, but yeah, most of the time, if you have a fifth order system, for example, it would need 5 zeros to cancel out these poles. It's quite interesting to think about that. But other than that, PID controller design depends upon basically the practical application itself, but also you have to kind of see what the method is trying to do. Or sometimes you have to use pole zero cancellations, sometimes you want to avoid them. So you have to get this feeling of the PID controller to what to do. And in practical applications, you're not going to use the PID controller on its own like it is. You have to go for some connections and special limitations. And one of them is going to be the control signal, which we will be looking at next week. I guess the topic of next week is going to be the control signal. We will be talking in much detail about the control signal. So that's it basically for this week. If you have any questions, feel free to ask. If not, we'll see each other next week, same day, same hour.